Hey guys, welcome to another CNCM lecture. This one's on combinatorial identities. So the basis for everything we'll do in this lecture is centered around binomial coefficients. I'll assume you're already familiar with them, but if not, we'll have just a short discussion on them. So the binomial coefficient n choose k is the number of ways you can choose k objects from a set of n distinct objects. So I don't know if you have 4 balls, each labeled with their corresponding number. You can choose 2 of them in 4 choose 2 ways, which is 6, using this formula. Alright, and you can put these binomial coefficients in what's known as Pascal's triangle. So which you see in this image up here. So the 1 corresponds to 0, choose 0. The one down here corresponds to 1, choose 0. The one over here corresponds to 1, choose 1. Here it's 2, choose 0. The middle is 2, choose 1. Over here you got 2, choose 2. Yeah, you get the picture. You'll notice that the triangle is symmetric because n choose k equals n choose n minus k. And the most interesting property of this triangle is that 2 consecutive numbers along a row, when added together, form the number below them. So for example, you have the 6 here and the 4. Oops. The 6 here and the 4. My God. The 6 here and the 4 here add up to the 10 here. The 1 here and the 5 here add up to the 6 here. The 6 here and the 1 here add up to the 7 here. You get the point. Alright. Algebraically, that property of the triangle can be written as this equation. N minus 1 choose k minus 1 plus n minus 1 choose k equals n choose k. The algebraic proof is given here, but the more interesting proof is the combinatorial one, which can be shown as follows. Suppose you have n people, p1, p2, p3, all the way up to pn. Suppose we want to choose k of these people. There are obviously n choose k such ways to do so. But there's another way you could imagine choosing k people. We split it up into 2 cases. What you can do is you can pretty much cordon off the first person and do casework based on whether or not you want P1 to be one of the k people you choose. So the first case is P1 is chosen. That means of the remaining n minus 1 people, we have to choose k minus 1 people so that together with P1 they form k people. So in this case we have, let's see, of those remaining n minus 1 people, you have to choose k minus 1 of them. In the second case is p minus 1 is not chosen. Well, if you don't choose p1, then of the remaining n minus 1 people, you have to choose k of them. All right, and if you just add these 2 cases up, you have to get n choose k. And this is known as Pascal's identity. All right, on to the hockey stick identity. So the hockey stick identity says that if you start off with r choose r, and keep increasing the number at the top. Say you keep going r plus 2 choose r all the way up to n choose r. Then you're going to get n plus 1 choose r plus 1. If you go back to Pascal's triangle, there's a nice interpretation of it. So what you can do is you can basically move across a diagonal and make a turn like you have a hockey stick, and the number at the turn is going to be the sum of all the numbers that were on the diagonal. So the 1, 3, 6, 10, 15, 21 you see here, all of them add up to 56, which is the number at the turn. You can at the turn here. So quick clarification. The summation you see here doesn't quite correspond to the blue numbers you see in Pascal's triangle here. They actually correspond to the reflection of those numbers. So it's this hockey stick that corresponds to this identity, not the blue and red one here. So you can prove it. You can prove the hockey stick identity using induction, but the easier way is just by looking at Pascal's triangle and noticing that the 56 that you see here is the sum of the 35 and the 21. All right, 35 is the sum of the 20 and the 15. The 20 is the sum of the 10 and the 10. The 10 is the sum of the 4 and the 6. The 4 is the sum of the 1 and the 3. And the 1, well, that's just a 1. That corresponds to the 1 above it. So basically by repetitively using Pascal's identity, you can work your way up Pascal's triangle and just notice that the sum of the diagonal is simply equal to the number at the turn. So at the end of the day, if you work your way up, these are the numbers you get. All right, on to Vandermonde's identity. So the summation it says that m plus n choose k equals the following sum. M choose 0 times n choose k, m choose 1 times n choose k minus 1, m choose 2 times n times k minus 2, all the way up to m choose k, n choose 0. Alternatively, you can write the summation as the sum of all non-negative integers a and b that add up to k, and then m choose a times, n choose b. It's the same thing because you'll notice that the 2 and the k minus 2 add up to k, the 0 and the k add up to k, the 1 and the k minus 1 add up to k. So it's just across all non-negative integers that add up to k. And the proof's also actually fairly simple. In light of this summation here, we are going to do as follows. Suppose you have a box. In the box, there are A red balls. Actually, sorry. I'll move the proof along in black. You have a box. In this box, there are A red balls and B blue balls. I'm sorry. Alright. Okay, I'm sorry. Whoops. That's not right. I'm sorry, in this box there are m red balls and n blue balls. They correspond to the m and n in the identity here. So you have m red balls and n blue balls, and in this box there are a total of m plus n balls, and you want to choose k balls. Well, there are obviously m plus n, choose k ways to do so. But the other way you could choose these balls is by splitting up these k balls into desired amounts of red and blue. So what you do is you say, all right, suppose of the k balls we choose, a of them are red, and you let b of them be blue. And obviously, they have to add up to k because you're trying to choose k balls. But now that we've done this, of the m red balls, you simply choose the a that you want to be red. And of the n blue balls, you simply choose b of them that you want to be blue. And in total, you have these a red balls and b blue balls that you've chosen that together form k balls. And if you just start varying a and b over all possible numbers, non-negative integers that add up to k, then you get exactly m plus n choose k. And then this is exactly Vandermonde's identity. All right. Finally, we'll finish up with committee forming arguments, and the best way to illustrate this is through an example. So suppose we want to prove this identity here. The summation in the left-hand side corresponds to the following. So suppose you have, again, n people, p1, p2, p3, all the way up to pn. The n choose k corresponds to choosing a k-person subcommittee that's the n choose k. And from this k-person subcommittee, you choose its leader. Well, since there are k people in the subcommittee, there's k ways to choose the leader, or there's k choices for the leader. All right. So that's where the k times n choose k comes from, and by adding up from k equals 1 to n, essentially what you're doing is the summation corresponds to the number of ways to just pick a subcommittee of any size and pick its leader. So again, the summation on the left-hand side corresponds to picking a committee of arbitrary size and then choosing its leader. All right, but there's another way that you could do this. You could instead choose the leader of a committee first, and then decide whether or not the rest of the people should belong to this committee or not. So on the right-hand side, the n here corresponds to picking one of these n people here to be the leader. So for example, if you choose P1 to be the leader, then the 2 to the n minus 1 will correspond to deciding whether or not P2 should belong to this committee or not, whether P3 should belong to the committee or not, all the way up to figuring out whether or not Pn should belong to this committee. Since you have two choices for each of the remaining n minus 1 people, this is 2 to the n minus 1. All right, and then but once you've decided who the leader should be and who should be in the committee, then you fully formed a committee. So this identity has to hold true. I encourage you to think about what happens if you instead replace this k with a k squared. and try to prove this second identity here. All right, that's it for this lecture on the theory. We'll have a few examples of harder AME problems in the next lecture. Thank you.